Good morning, everyone. Welcome back to the lecture number 4 of this course. So today, this lecture is going to be a follow-up from Taco's lecture a few hours ago. So we are going to continue discussing about geometric priors and how they hopefully make machine learning easier in high dimensions. All right. So today, in this lecture, we are going to the first thing we are going to discuss is how these ideas from symmetries and invariances relate to the problems that we discussed in the lecture number 2 that concern the curse of dimensionality. Then we are going to move from the notions of invariance to notions of scale separation. So we are going to discuss another prior. And then we are going to combine these two priors, invariance and scale separation, into what we call the geometric deep learning blueprint. Okay, so that's what we're going to do in this hour. All right, so let's start with the first one. So remember, the goal of machine learning, in particular in the case of supervised learning, is to learn an unknown function f star, right? So remember, the notation is that this function f star is defined over a very, very high dimensional space. X would be the space of all possible images, for example. And so remember that one of the the conclusions that we had in the lecture number 2 and that Taco started to discuss is that if we just stick with this black box thinking that X is a very high dimensional space, well, basically there's nothing we can say, right? The learning is always going to be fundamentally hard unless we make more assumptions. And so in this context, what the kind of assumptions that we make, they rely on what we call opening this box, right? So not treating the input space X as a black box, but seeing X as the space of signals, small x, that map from a geometric domain omega to some space of channel, right? And here there's a little illustration where what I mean, right? The domain now becomes here in this particular case a 2-dimensional grid. Okay, so that the thing is that here capital X is a high dimensional space, but the input space here, the geometric domain omega, is a low dimensional space, right? In this particular case, it's just 2 dimensions. And so once we have this domain, this 2-dimensional, like low dimensional structure, or more generally, we have like a domain and a mathematical object that is much simpler, we can do many things with it, right? And these geometric domains, they come with kind of a natural class of transformations, right? There's things that we can manipulate, like the objects in omega can be manipulated in ways that are very, very simple. For example, if I have a collection of elements in a set, well, there's a transformation that is very natural in a set that is just to shift the elements, right? To permute the elements. Or if I have points here in this grid, in this 2-dimensional grid, I can move the points, right? I can translate any pixel from one location in the 2-dimensional space to another location. Okay, and I can do that either with a rigid motion, like Euclidean transformations here, or I can do it even with what we call a warping or diffeomorphism, right? So every point, every pixel in my domain is moved in another place. And what Taco discussed this morning is that once I have a collection of transformations, well, I can suddenly start to do very nice things, right? I can compose them. I can apply transformations one after the other. And these transformations, they form what we call a group, right? There's a algebraic structure that emerges very naturally in this context. And so here's another very interesting thing that you can do with these transformations. And I also think that Taco discussed that, is that once I know how to move elements in my geometric domain omega, right? Like points in a grid or elements in a set, then I can upgrade, I can kind of use these transformations to transform much more complicated objects, which are the signals on the domain, right? Like these. So in other words, I can go from a transformation that moves things in my low dimensional space omega to the same transformation, right? That moves things in a much, much higher space, right? Like the space of signals that live in that domain. And the natural way to extend these transformations is by composition, right? And so here, the example that you see is like, let me see this picture, right? So if you look at here to the right, a transformation that is just moving pixels around, right? If I apply this transformation now when I have images, right? Hopefully you should be able to see that. These are some rotations that I can apply to my image, or I can apply some deformation, right? As in this video that you see, right? So So here's an example of a transformation that is defined in this two-dimensional grid that now I can apply it to transform my input in my high-dimensional space. Okay, and this not only this, the transformation that I have in this high-dimensional space is linear. Okay, and I think that Taco maybe gave you the right language for that. It's called a group representation, right? So this is a transformation here you see in the left-hand side that is linear with respect to x. All right. So so now let's try to like natural first question is, okay, now we have these invariants. How can we connect the notion of invariance with a statistical learning, right? With a problem of learning that we discussed 2 days ago. So remember, we have this function that we don't know and we want to learn, and we are trying to learn this function within a class, right? This capital F was a class of a class of functions, for example, things that we can parameterize with neural networks. And so here's a promise, right? So now I assume when we make this, this assumption that the function that we don't know that we want to learn is invariant with respect to some group, right? So it means that for any input in our space and for any transformation in our group, the function is the same if we apply x, if we apply the group transformation to the any input. Okay, so this is an assumption. This is a kind of a prior that I promise you, right? So you know that this is true all the time. So natural question, if this is true, there are two natural questions, right? So okay, how can we now leverage this assumption in our hypothesis class? Can we do better now that we know this extra information? And obviously, it's like, okay, even if we can do better, can we do good enough so that we can break the curse of dimensionality, right? Like the major issue that we had, where any kind of quantitative guarantee was always very hard to get in high dimensions. Okay, so is this clear? Yeah, and again, please do not hesitate to stop me for any questions, because I don't see you in the camera, so please do not hesitate to interrupt. All right. So these are the two questions that we are going to study now. Okay, so first, let's forget about the algorithm. Let's forget about implementing anything. Let's just think about abstract, like theoretical, right? So how can we now use these invariants with respect to this group of transformations to do better machine learning, right? To learn more efficiently. So the first idea, right, is to use what we call this smoothing operator. Like we are going to use the group of transformations to have a way to smooth functions. And so let's assume for simplicity that the group is discrete, right? So we can just, go through the group by just summing all the elements. And so given any function f, this is like the target function, or like any function that we want to parameterize in our network, we are going to define its smooth version as the average of the function over the elements of the group, right? So in coordinates, if you think about what happens here in this equation, for any given input x, the output of my hypothesis is not going to be f of x, but it's going to be the average over the what we call the group orbit. And what is the group orbit? Is all the possible transformed versions of x, right? So this is what you have here in the right hand side, right? So I'm basically, I have any function that produces labels. Let's say that I have I take AlexNet or whatever, right? Like any network, and rather than using the output of AlexNet at this particular image, I'm going to average over all the predictions that the network does over all the possible rotated versions of this image, right? That's what this operator is doing. So now I ask the question, if I apply this smoothing operator to my function f star, what do I get, right? So remember that the assumption that we have on f star is that it's invariant, right? So remember what is the definition of invariance, is that the function f star is the same at x or at any transformation of x. So this means that the function f star, when I look at it along each of these orbits, gives me something that is constant, right? Doesn't change. So what happens if you have a function that is constant and you average it? Nothing changes, right? So a function that is constant along the orbits, if I do the average, nothing changes. Okay? So so now let's try to build on this observation. Okay, so now, well, if I know that my function, target function doesn't change by averaging, here's a natural idea, right? Given any hypothesis class, this could be, let's say, the family of fully connected neural networks, we can make it invariant by applying the smoothing operator, right? So any function in my family, now I'm gonna, instead of using it directly, I'm gonna use the smooth version of this function, right? Why? Because the target doesn't change. So I'm gonna consider it in my hypothesis class. So here's an example, right? So let's consider the domain, the discrete domain of the points, right? Like say a one-dimensional grid. And here I'm considering as a group of transformations the translations, the shifts. Okay, so this corresponds to the group that is called the cyclic group of order D, right? And I assume that once you shift this point, the last point, you go back at the beginning. Okay, and now I consider as my hypothesis class F all the polynomials that I can build with the coordinates of degree K. And now let's think about what would we get if we take these polynomials and consider the smooth version. So there's a question for you, right? But think about how you would now take any one of these functions and consider its smooth version, right? So remember that a smooth version, right, should be invariant, right, with respect to all the translations, like all the shifts, right? So think a little bit about how would that do. And obviously, this smoothing operator, if you change the group, right, if you, let's say, replace the group of shifts by maybe a much larger group, like the group of all possible permutations, then this function, right, the invariant function class will become small, right? So here the bottom line is that if I have the larger the group of transformations, right, like the larger the class of invariants, the smaller is going to be this set, right? So there's less and less invariant functions, right? The larger the group is. I hope this is clear. Okay, and these are two little exercises that I leave for you if you wanna try to think about the answer. I'm ready. I'm also, of course, available in Campus Wire. All right, so now let's try to to argue the following, right? Is that the approximation error is not affected by smoothing on the group, right? So I claim that if now given a target function f star, if I try to minimize the error, right, in my family class, right, in my function class capital F, what I claim is that I pay no price if I reduce the hypothesis space from capital F to its smooth version. Okay, and why is that? Well, the reason why is that in fact this operator, right, the smoothing operator, is a projection. Okay, I'm just essentially I'm decomposing the space along the orbits and just keeping the average along each orbit. So in fact, it's an orthogonal projection, right? And so what I can do is that any error, any L2 error, I can break it into the error that I make in the range of the operator plus the error that I make in the complement, in the orthogonal complement, right? And this is nothing else than the Pythagoras theorem, right? Because this is an orthogonal projector. And so because now my function f star is invariant, right? What I see is that because the function is invariant, this term disappears, right? When I replace g by f star, this term disappears. So my error that I make, right, has two components. Is the error that I make on the invariant part plus I pay the price how an invariant is. So obviously from this equation, you can immediately see that I'm better off just assuming by construction that the yellow term here is 0, right? That this term doesn't appear. And so obviously I have something that looks like a winning strategy here, right? Because I have a function class, the one in green, that has the same error, the same approximation error, and because the green space is smaller than the blue space because it's a projection, I will have smaller statistical error, right? So I have the same approximation error and smaller statistical error. So it means that it's better. But the question is by how much, right? Is it a gain that is minor, that is marginal, or is it a gain that is substantial? Any questions so far? Okay. Okay, so now let's try to do a little bit of quantitative statements here. This is possibly maybe the most technical slide of today. So hope bear with me. So remember from two lectures ago, the class of functions that were Lipschitz, right? That were just locally regular, right? And now we are gonna, yes.
So there was a question on campus wire. Someone was asking.
Perfect.
Okay, please can you explain what is a group smoothing operator?
Okay, yes, that's very important to understand this concept. Yeah, so let me go back to the definition. Good. So the group smoothing operator is an operation that I make to a hypothesis, to a function that maps input to my machine learning model to the output. Okay, and it's an operator that does the following here in this equation, or maybe you can look at this equation that is even more clear, is that given an input x, I'm going to consider all the transform versions of x, right? This is what we call this orbit. Look at this picture, right? So think of it as some kind of data augmentation, right? So you have all the possible transform version of the input. Then I'm going to apply my network, my hypothesis F, to each of them, and then I'm going to take the average. That's the group smoothing operator, right? And this group smoothing operator has a immediate property. There are two things that are important. The first one is that it's an orthogonal projection, right? So you can think about it that if I apply the smoothing operator twice, I get the same thing, right? If I smooth 2 times, I get exactly the same output, right? Because the function, right, these orbits, by definition of a group, right, they are the same irrespective of where I start. And the other property that is important is that when my function f star is invariant in the first place, right, then when I apply the smoothing, nothing changes, right? Because if I have a function that is already constant along these orbits, a constant function, if I apply the average at every point, doesn't change, right? Because the function is already constant. Okay, I hope that this is clarifying the definition and the concept of group smoothing operator. Very good. So now, as I said, I can consider like the smooth hypothesis, right? For everyone.
There's another question.
Yes.
So another
question. Go ahead.
What is the cyclic group?
Cyclic group. So that was an example that was
the different axioms.
Yeah. So the cyclic group is a particular group that is, think about the arithmetic modulo D, right? So think about like, let's say the numbers like binary arithmetic, right? Like you have binary numbers, right? So 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 1 equals 0, right? So this is an example of a group where I can think about this some kind of additive group, but the only difference is that it has a kind of a periodic boundary condition, right? Is I can every time I arrive at the largest number, I go back to the beginning, right? That's what's called a cyclic group. Yeah. Any more questions? Okay.
So you can continue.
Continue? Perfect.
Yes.
Good. So I was here. Okay. Right. So this is the setup that where now we are going to try to quantify a little bit this game. So remember that we had this space of functions that was very, very large, the space of Lipschitz functions. And the conclusion from lecture 2 was that this space of hypothesis was far too large, right? In the sense that there was no way we could guarantee that we can learn functions in this class with a number of samples that is not exponential in dimension, right? So it's like a massively, it's a set that is very, very large. So now let's try to make it smaller. Let's try to add this hypothesis of invariance. Right? Let's try to see if we can suddenly start to learn with more efficient, like with smaller sample complexity, if we add invariance into this Lipschitz hypothesis. So now my hypothesis is that this function f is going to be Lipschitz, right? But also it's going to be invariant with respect to a group of transformations, right? So it means essentially that this function f of x minus f of x prime, right? If x and x prime are in nearby orbits, right? Then the value of the function doesn't change too much. All right, that's the notion of Lipschitz plus invariant. So here's a result that we we worked on with a couple of collaborators from my group that says that, okay, if we now try to learn with essentially with the optimum model, machine learning model for learning Lipschitz functions, which is kernel methods, and we use a kernel that is invariant with respect to action of G, indeed, we can do better than if we don't use the group invariance, right? So in other words, this is the generalization, like this is the test error of our learning. Is gonna have a generalization error that essentially it's as if the algorithm, instead of using n number of samples, was using n times the size of the group. Okay, so in that sense, it's as if the algorithm is better, right? Because it's as if it was using more data points, right? There's a gain in sample complexity, which is consistent with the intuition that we have so far, right? That the approximation error doesn't change, and the generalization error has to be better, right? So that's what we see here. But there's a big problem. There's a problem here, right? Is that even if this number here that you see in blue is very large, let's say that it's an exponential in dimension, right? This exponential in dimension is going to be killed by this rate, right? So here you see that the dimension is in the denominator, right? So if we have something here that is exponential in d, this d here is going to be killed by this d here, which means that the rate, the gains are like the rate in number of samples is not going to change, okay? So the rate of learning, like the generalization rate, is still cursed by dimension, okay? So the only thing that invariance give us in this context is a gain in the constants, right? We can do better, but the kind of the major problem that we had before still remains, right? We still have this very bad dependency on dimension for this class of regularity. And let me also say that the gains that we see here relative to not using the invariance are real, right? So if you use a kernel that is not invariant, then actually you cannot reach this generalization error, right? So there's actually a sharp contrast between invariant and non-invariant kernels. Okay, so but the conclusion here, right, is that if we use them, if we use invariance in our networks, we are going to do better. That's a guarantee that I tell you. But so there's an improvement in sample complexity, but there's two things that are that we still need to address. The first one is that it's not sufficient, right? It's necessary, right? But it's not sufficient, right? We need some other tool to guarantee that we can learn with a number of samples that does not blow up with the dimension, right? There's something missing. What is missing? And the other, right, is that so far this analysis that we have made, right? We have made everything from this smoothing operator, right? And this seems like a kind of a very abstract concept, right? There's no easy recipe for implementing this operator in practice in your algorithm, in your computer, right? So how can we build these invariants in a way that is efficient, right? That is, that we can implement and this thing runs efficiently. Okay, so these are the two important things that we are going to discuss next. A good time also now to make a pause and ask for questions, because I cannot access CampusWire in real time. So yeah, if there's some questions either here or in CampusWire, happy to address them now. Otherwise, I will move on.
Yeah, please, I think we can move ahead. There's no questions right now.
Perfect. Perfect. Thank you. All right. So now let's move to the second part of the lecture, which is addressing the missing ingredient, right? Which is the notion of scale, multi-scale separation. Okay. And so if you think about why deep learning works and what is the kind of the secret sauce of these architectures, and you go to, to the lectures of the one of like the pioneers of the field, like Joshua Benjo or Jan LeCun, you see that their arguments, they all involve this notion of compositionality, right? Like the fact that you can actually break a very complicated input, right? Like a kind of image that has millions of pixels, you can process it in ways that are step by step, right? So first you can focus on maybe local features, right? What they call these low-level features. Then these low-level features are combined into more complicated structures and so on and so forth, right? And in fact, this is a very intuitive idea, right? That it's present in deep learning, but of course it was present in many other areas before, right? Like even people doing computer vision have exploited this idea, and in fact, this is an idea, right? This compositionality is an idea that is, in a sense, at the core of science and physics, right? So like the idea that we can process very complicated phenomena by breaking the problem into different steps, right? Like first, let's look, for example, at biology, okay? Or yeah, exactly, biology or any kind of like a chemical process, right? So there's actually ways in which you can first understand how, how things behave at the level of subatoms using quantum mechanics. Then at some point you need to understand a little bit of chemistry, right? Maybe at this level, and then at some point you need to start understanding things about biology, right? Like how molecules become proteins, and then proteins become cells, and then you see the idea, right? And this idea is present in many areas of physics, like when people study turbulence, or when people study like a percolation phenomena, critical phenomena, even in in many areas of data science, we also have this idea. Okay, so when we are facing a complicated problem that has many dimensions, natural idea in science, try to break it into smaller pieces. Very natural. So in our context, right, we can formalize this intuition with what we call the multi-resolution analysis. Okay, and for simplicity, I'm going to just illustrate this principle using a two-dimensional grid, the grid that you see here on the right. Okay, so I think that the main idea, right, is that if I have any signal or any structure that lives in this rectangular grid omega, there's the idea that I want to communicate, that I want you to get, like the vision, is that I can always change the resolution, right? I can preserve the information that I see by changing the resolution, right? You do this all the time when you have you take a picture with your phone, or and then you want to send it to your friends. You can send it, you can choose the resolution, right? You can either send it in full resolution, it's going to be very, it's going to take a long time, or it's going to take a lot of space, or you can compress it and make it smaller. So this is actually instantiated mathematically in what we call a multi-resolution analysis, right? So what is a multi-resolution analysis? Like, broadly speaking, is that it's a process by which you take any signal, like any image, right? It's like this signal that lives in this two-dimensional grid, and we can decompose it into a signal that lives in a coarser resolution, right? Like here, the idea that I try to illustrate is this like resolution in orange has less pixels than the grid in gray, right? And so I can express an original signal X in terms of the coarse version, right? But of course, when I go from the gray cell like grid to the orange grid, I'm throwing information, right? I'm using less number of pixels. So the multi-resolution analysis, what it does is it also keeps the details at a given resolution omega that I need to reconstruct. So it's really this process where I start from this like original image here, and then I break it into the low resolution version, that is this one here. And then I need to keep the information that I need to go backwards, right? To go from the coarse resolution to the fine resolution. So in other words, I need to preserve the details, right, that are encoded in this image here and this image here. And these details are what is captured by what we call wavelets, right? So wavelets are essentially a bunch of filters that extract, that really do this decomposition for you, right? And this is actually something that we are going to discuss with a little bit more detail in lecture 7 when we are going to talk about grids. But the key property that for now you need to, I want you to remember is that these filters, right? These wavelets, they are think about these as little waves that are localized in space, right? Rather, it's very different from a sine and cosine, which are waves that keep going, forever. Wavelets have a different properties that there's kind of little waves, like waves that are localized in space. And this is actually these wavelet decompositions are very important in many areas of, beyond computer vision, but they are used in many, many areas of science, right? Anyway, all right. So what is the link between this decomposition of, this way of thinking about images in terms of different resolutions and our learning problem? So here's an example, right? And this is really what we call the scale separation prior. Okay, so let's see how the resolution of the input can give us a different category of priors. Okay, so first, let's make the assumption that the target function that we don't know, right, f star, has a following property, is that the function I need to learn, and in fact, I could also learn it directly from the coarse resolution, right? So I don't need to look at the image at full resolution to understand the function. So here's an example. Let's say that we have a problem where f star of x just encodes the probability that, like whether I'm in a beach or in a mountain, right? Given the image, I just need to guess whether it's a beach or it's a mountain. Okay, so this seems to be a function f star. Perhaps I don't need to get all the details. I don't need to know, I don't need to see all the waves in the sea, and I don't need to see all the boats in the beach, and I don't need to see all the trees in the mountain to know that it's a mountain or a beach, right? So in other words, if now I remove the details and I just look at the coarse scale, right, for like as here, well, I guess that you can all still tell that in the top we have a beach, right, and in the bottom we have a mountain, right? So here's an example where the coarse scales dominate, right? So here I'm in a problem where essentially to approximate this function f star, I don't need to think about the function x, like the input x as being high resolution, right? So I can, indeed, I can just focus on the right-hand side. And what is the advantage of thinking of the function in terms of the low resolution? Well, the low resolution has much less pixels, right? It has a much smaller number of pixels. And so in that sense, the number of, the number of like the dimension of the input is much reduced, right? So the course of dimensionality in that sense is reduced just because I can, replace the input by something that has much smaller dimensionality. Okay, is this example clear? Okay, here's another example for you. And obviously, but obviously this assumption, right, that I told you that I can always kill the high frequencies is not true in general, right? This is only true in certain cases, right? So if I think, for example, as another example, recognizing these MNIST digits, right? So you can all look at the MNIST digits here, right, and probably recognize the digit. But if I blur, right, so if I remove the high frequencies, right, as I did here in the right panel, for me it's impossible to tell what is the digit. Okay, so what it means is that this assumption that I just made about the this example of the beach and the mountain is a very strong assumption, right? This cannot be the basis, right, of geometric deep learning, right? We need to be careful. So here's another flavor of this equation, right? So there's another thing that we can assume, right? Instead, that the target function, I can construct it, I can approximate it in a way that I can think it as a linear combinations of functions, G, that instead of depending on the full image, they only depend on local patches of the input, right? This is an example of these textures that I showed here, right? So if you want to, separate between a brick wall and a patch of grass, well, I guess if you just extract a couple of windows from the brick wall and a couple of windows from the patch of grass, you can already see, right, that 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 you can separate these two classes, right? You don't need to see the whole thing to realize that it's a grass or a brick, right? You can only look at local scales. Okay. So this is an example, another example where we can also break the course of dimensionality, right? Just because obviously here the dimension that matters, is the dimension of the patch, of the yellow patch. It doesn't matter the dimension of the whole thing. Okay. So here's another example where we can still avoid this course of dimensionality by making this assumption. Again, is this assumption realistic for any general problem? What do you think? Well, this seems pretty strong, right? So this example works for the case of these two classes, these two textures, but probably doesn't work in general, right? Like here's an example. Okay, so actually, sorry, before showing the things where it doesn't work, this assumption is in fact also quite used in many problems in physics, right? Like this locality, right? The fact that the local interactions dominate is a principle that is very common, right? In many areas of science. But of course, it's also a strong assumption, right? Here's like a little example that I took from this paper by Turk, where if you just rely on the texture, on local properties, right, you are missing kind of the global appearance of the problem. Like you can, in a sense, build examples where you still need to see all the image at once to realize what happens, right? So what we see here is that there are kind of different extremes, right? Like that either we make an assumption that the coarse scales are the only thing that matters, and then we can see that the problem is easy, or we can say that the local scales are the only thing that matters, and then the problem is also easy. But neither of these two assumptions seems to be, realistic enough, right? There's always problems where none of these assumptions is going to be true. So what we can do is, in a sense, more generally, we can consider kind of a mix of the two, right? So we can consider a model that this is like this notion of compositional model, right? We can try to think about our function f, right, that we are trying to learn as a composition of two functions, okay? So first we have a step that we call this p, or like a coarsening, right? That is what the role of this step is to reduce the size of the grid, right? Or the coarsen the domain omega, okay? And then once we are in a coarse domain omega, the idea is that we are already in a regime where the course of dimensionality is somehow avoided, right? So we can now learn in this function f tilde, hopefully with a sample complexity that is not as bad as the original domain. Okay, and the key point, right, is that in general we need these two guys to be trainable, right? The assumption that I made before, like the two extremes, where in one extreme I just told you that this object here, this P, is actually a linear coarsening, that there's no training. That was the first example. And in the second example, I just gave an example where this F tilde was just like an average, like a global pooling, like an average pooling without anything else. Okay, so in general, we are going to be needing nonlinear models that are trainable in both of these steps. Okay, is this a separation? Is this scale separation prior clear? Any questions? Otherwise, I will move on. Okay, so natural question, of course, is, okay, now we have introduced this framework, that is this model to learn functions as a composition. When is the composition more efficient? Okay, and this is again the intuitive idea that Joshua and Jan and everyone has been developing. So there's actually several frameworks where we can study this question of benefits of composition quite precisely. Okay, so for example, in dynamic programming, we have this framework of divide and conquer, right? Like this strategy to solve like algorithmic tasks by breaking them into smaller tasks and then aggregating, right? So this, in many for many algorithmic problems, dynamic programming is an example where we get basically best, good efficiency. In fact, in the context of learning, these benefits of composition are, I would say, it's fair to say that they're still not completely well understood, right? So we have intuition that these models should be more efficient, but we don't have very mature math to explain why, Okay, and this is in a sense a work in progress. Okay, but what we're gonna settle is that in any case, this prior of scale separation, this view of looking at the problem, looking at parameterizing functions as a composition, in a sense, it can be combined very naturally with the other prior, which is the prior of symmetry. Okay, and so that's what we are going to see right now. Okay, that's the third part, which is the blueprint, the geometric deep learning blueprint. Okay, I will pause again before moving into the last part for if there's any question. Okay, so now that we have seen the two fundamental geometric priors, like invariant in the first place and then scale separation in the other place, let's try to see how we can combine them, okay, into an architecture or a blueprint that we can use across many different domains. Okay, so remember the wish list that we want, right? So we want our function class to be invariant to the transformations, just because we have seen that it always helps. We want to have multi-scale structure because we need it to break the course of dimensionality. But of course, we want this class of hypothesis to be very rich, right? To be very expressive, right? We want to be able to approximate like a large class of target functions. Okay, so how can we build an architecture that satisfies these three properties? Let's start with linear functions, right? Linear invariants. So we can first try to understand, try to enumerate or to describe all the possible invariants with respect to a group, okay, that are linear. So how many are there? In fact, there are not so many, okay? There's essentially only one operator that is linear and invariant to the group. And this is exactly the operator that we just saw before, right? This is basically the average along the orbit, okay? In fact, you can see that any operator F that is both linear and invariant, in fact, has to be a function of the group average already. Okay, and you can see it here. There's basically two steps here, right? So like in the first step here, the first equality, we are using the fact that it's invariant. And in the second equality, we are using the fact that F is linear. Okay, so you can see that the object that appears here is the group average. Okay, so the group average is basically the only linear operator that gives us invariance to the group. But of course, this is not an operator that we can use for many things, right? Because it's an operator that is very lossy. Imagine here, right, in this example of the phases, right? If I look at the average of all of these phases, right, across all rotations, I'm probably going to be losing all the information I care about. Okay, so clearly we need to have something that complements this average. So how can we complement it? So it turns out that the natural way to complement, the right way to complement invariance is by looking at linear equivariance. Okay, and I believe that Taco already described what equivariance means, right? But just for security, let me just recall the definition, right? So if I have a group that is acting on both the input and the output of this mapping, right, mapping B, then this mapping is equivariant if essentially the group action commutes with B, right? So if I apply the transformation in the input right here and I apply B, I get the same thing as if I first apply B and then apply the transformation in the output. Okay, and there's many examples. I mean, this concept of equivariance is central. It's going to be very central in this course, right? We are going to see it again and again and again and again. So now, let's see what I can do with linear equivariance. Okay, so and for that you might ask, okay, but remember that the goal we had at the end of the day is to learn invariant functions, right? That was our wish list, right? If you go back here, the wish list was to get invariance, right? So what is the relationship between equivariance and invariance? So you might say, okay, maybe I can take one of these guys that is equivariant and then compose it with the group average, right? Do I get something different? So if I take a linear equivariant and then I apply the linear invariant, does it help? Well, you can already see the answer, right? It doesn't help. Why do you think it doesn't help? I combine, so the goal here is to build more invariants, right? And so I suggested maybe we can look at equivariants. So if I take one mapping that is equivariant with G, that is linear, and I compose it with a linear invariant, the one that you had before, this group average, do I get something new, right? Do I get like a new invariant that they didn't have before? And the answer is no, right? Just because when I compose a linear equivariant with a linear invariant, I still have a mapping that is linear, right? The composition of two linear maps is still linear. And we just saw in the previous slide, right, that basically the only linear invariant is the average. Okay, so if I start composing operators that are linear, I'm not going to get any more expressivity. Okay, so the alternative, right, and I guess that this is hinting the answer, is that I need to go nonlinear, right? We need something that that we need something that makes the operator nonlinear. But also, of course, we need to apply something nonlinear that doesn't break all the other properties that we are trying to build, right? In particular, doesn't break the invariant or the equivariance. And so what is like the answer here is to consider operators that are nonlinear, but that only act element-wise, right? So these are transformations that we call raw that map images to images in a way that the transformed image at pixel u is only a function of the image of the value of the image at pixel u, right? So here's an example to illustrate what I mean. For example, think about an operator that changes the color, right, of each pixel. This transformation can be nonlinear, can be anything you want, but of course it's a transformation that looks pixel one by one and applies the same mapping pixel after pixel, right? It doesn't depend on the ensemble of pixels at the same time. And so now I'm in business, right? Because now what happens? If I take a mapping B that is linear and equivariant to G, and I compose it with one of these guys, one of these element-wise nonlinear mappings, I have a new operator, this B tilde, and I claim that this operator is still equivariant. Okay? And why would that be? Why is this operator equivariant after the nonlinearity? Well, because of this property, right? Remember that an equivariant function, right, is to verify equivariance, I need to make sure that if I apply a group transformation, right, so on before B tilde, I get the same thing as if I apply the group transformation after B tilde. But because this operator B is equivariant and this operator rho only looks at pixels individually, right, I get this commutation property, right? And I think this is an important exercise that I encourage you to verify by yourself, okay? And so the point here is that now we are kind of culminating into the blueprint, is that now we have now at our disposal kind of three important building blocks, right? Like just focus on these three for now. Okay, the first one is if we can take an operator that is linear and equivariant with respect to the sum group G, then I can consider a family of operators that are nonlinear but element-wise, okay? And then I have an operator that is invariant with respect to G that can be linear, right? This is global pooling. Okay, so now the point is that if I have these operators, I can start combining them, composing with each other. So I can start creating a very, very rich family of transformations, right, that satisfy my wish list. Okay, because from what I said, if I take a green, a guy that is green, and I compose it with a guy that is blue, I still get something that is equivariant, right? And if now I compose it with something that is orange, I get a new invariant that is different, right, from the original pooling, okay? Because now the nonlinearity is really introducing other information, okay? And the important point that I want to stress here is that the way we define these operations is very general, right? In the sense that we can apply it for many, many versions of this domain, right? So depending on the domain omega and the group of transformations G, right? Here's a recipe where the only thing that we need is to understand the class of linear equivariance of that class, right? So given an omega and a group, we just need to understand the class of linear equivariance. And it turns out that this is something that we can do in many, many different domains, right? This is like a little diagram. And here's an example, right, of the different combinations, of the domain omega and the group G. Okay, so if we take as the domain the grid and we look at the translations, the blueprint gives us convolutional neural networks. If we take rotations and the sphere, we get the spherical neural networks, et cetera, right? So the same principle that I just described, which is first understand the class of linear equivariance, and then compose them with element-wise nonlinearities and keep composing. This gives all these different model architectures here, right? And they are all following the same principle. All right. So just to summarize what we discussed today, and then we can have spend some minutes for questions. So what we have discussed is two geometric priors, right? The invariance with respect to some group of transformations, and then the scale separation, okay? And these two priors have to be combined, right? So if we don't combine them, a priori, there's no hope that we can learn in high dimensions, okay? And so what we have seen is that through this notion of group invariance and equivariance, we can produce an architecture that is this GDL blueprint that is a kind of a first principles architecture, right? It's a way to construct representations that have all the properties that we want, namely that they respect the multi-scale prior, they are respecting the invariance prior, and that they can be very expressive, right? That they can approximate very complicated structures. So what we are going to discuss in the next lectures by my colleagues, by Petar, Taco, and also Michael and myself, is that we are going to now, in the next lectures, look at this very general blueprint and make it concrete under different domains. And we are going to basically see how each domain brings its own specific properties, right? So here, in other words, in the surface, you might see that all these architectures are the same, right? They are basically have exactly the same structure. Well, because the grid, the sphere, and these groups have some different properties. These different in the domain and the group are going to induce differences in the architecture. And this is what we are going to describe in the next lectures. So now this is the end of my presentation, and I'm happy to take questions.